Okay, we're on the recording mode. And where we had left off last time was with the photoelectric effect. Here is a picture of the photoelectric effect, energy coming in and overcoming the binding energy of a bound orbital electron, setting that electron in motion. It's called a photoelectron, and that photoelectron has a particular kinetic energy, and the energy balance over here is as seen. Whatever energy comes in is split between the binding energy and the kinetic energy. The condition for this to occur is that the X-ray energy has to be greater than the binding energy. Down at the bottom of this slide is a little example of this energy balance equation, and it's asking, well, what is the kinetic energy of that electron? And given that 30 came in and 10 keV was the binding energy, well, the kinetic energy, as you can see, if you just plug in the numbers, would be 20 keV. What happens to that electron? It goes to dose. All electrons go to dose. With that little background, let's look at this one and go back to mammography and show how the that little balance equation answered the question that we had, or the principle that we had posed, and that was any material is transparent to its own characteristic radiation. In other words, when you put a filter in the beam that is produced by the same atomic number material, in other words, in mammography, we have a molybdenum target and we use a molybdenum filter. A very interesting thing happens. All the good energy, we had established that the optimal energy was 20 keV, and that's what the molybdenum target spectra concentrates at. But notice that you have low energies, you have high energies. We would like to get rid of them. So when you put a filter in, that molybdenum filter will knock out the lows, will down here, and will knock out the highs, but it will allow all of the good radiation to go through. The material, that filter, is transparent to the good 20 keV energy. Now, where did that come from? Well, first of all, notice that if you get rid of the high energies, that means that your subject contrast is going to get better. Your distinguishability of tissues will be enhanced. When you get rid of the low energies, lower than the 20 keV, then your dose goes down. So it's clear that it is advantageous for us to match the target with the filter. And but now the proof of why any material is transparent to its own characteristic radiation. Again, the binding energy was 20. Molybdenum has a binding energy of 20. The incident energy is 20, so that if 20 comes in and 20 is the binding energy, how much energy is available for the kinetic energy? 0, because you're matching the energy in, that's the characteristic radiation energy of 20, with the binding energy of the filter, which is 20. Nothing is available for the electron. The electron cannot get motion. It cannot have energy to move away. If it doesn't move away, it doesn't leave the orbit. If it doesn't leave the orbit, nothing happens. And essentially the interaction never occurred. So there it is. Any material is transparent to its own characteristic radiation. And concerning the characteristic radiation, remember that the maximum characteristic radiation energy is a transition from an electron that's not bound. That would mean it's out at infinity, or at least it's not bound to any given atom. And if that electron falls all the way down into the K shell, out comes the maximum characteristic radiation. Why? Because the energy that's emitted in the form of characteristic radiation is always a difference in binding energies. Well, there you would have the maximum difference. An energy at in infinity is 0, while the energy in the K shell is the greatest, so you have the greatest difference. And if you're looking at soft tissues, that binding energy is very, very low, less than 1 keV for typical soft tissues. Remember, soft tissue elements are things like hydrogen, oxygen, carbon, etc. And so characteristic radiation is easily absorbed. Wow. Now we can say that not only is that that kinetic energy of the electron totally absorbed going into dose, but now the characteristic radiation is totally going into dose. Okay, the photoelectric effect, and this is a big statement, always results in total absorption. Remember that the photoelectric effect was set in motion with the X-ray coming in, totally disappearing, and its energy totally appearing or reappearing in the form of characteristic and kinetic energy of the electron, and both of those are absorbed. So total absorption. Total absorption. And let's go on now to another feature of photoelectric effect, and that is, what's the probability of getting it? What are the chances of getting it? Is it very often? Well, how often you have this photoelectric effect depends on atomic number and energy. And here is the famous, what we refer to as the Z cubed over E cubed relationship. That's what characterizes photoelectric. And let me emphasize that cubic relationship. And a cubic relationship is an explosive relationship. But in terms of just the conclusion from this equation is that the higher the Z, the greater the probability of photoelectrics. So if you have something like lead, then you have a very high probability of interactions because lead has such a high atomic number. If you have tissues, soft tissues, that has a very low atomic number. So you have a much less probability of photoelectrics in tissues as compared to the higher atomic number materials. And notice there's an inverse relationship with energy. The lower the energy, the greater the probability. So that at low energies, you have much more photoelectric effects. And what's the importance of photoelectric effect as given by these equations? Photoelectric effects determine subject contrast. They determine the ability of a tissue to distinguish itself from the surrounding tissues. Now we can state to the photoelectric effect that not only do you get total absorption dose, but now that leads to subject contrast. This photoelectric effect is going to be exceedingly important for us. It determines dose and it determines how well you see tissues. That's the reason in mammography we went to low energies. Low energies over here, notice, if you go to low energies, the lower you go, the greater the photoelectric effect. Well, so what? Well, the greater the photoelectric effect, the greater the dependence on Z. And so when you have tissues that are very close to each other in atomic number, there's hardly any contrast typically available because the atomic numbers are so close. But if you go to low energies, those low energies overestimate or they exaggerate the subtle differences in atomic number. So now where tissues could hardly be resolved, now at low energies, like in mammography, they are visible. They can be resolved. So here's an example. We're given atomic number Z of 6 versus a Z of 12. By the way, don't have to remember it, but those are pretty much the difference between the soft tissues with atomic number 6 and bone with atomic number 12. But if you decide to go from 50 to 100, and well, first of all, let's take number 1. What if you change or compare 6 versus 12? What do you get using this relationship? Well, let's do it. In general, what we mean by that delta with that little r is a ratio difference, so that you would get the final divided by the initial, or whatever parameter you're looking at, whether it's the Z parameter or the E parameter. So let's do it. Determine the frequency of photoelectric if you go compare 6 versus 12. Let's do it. It's 12 over 6 cubed, which is 2 cubed, 8 times more difference. An atomic number 12 will give us 8 times more frequent interactions, using that little ratio down at the bottom of the slide. What if you go compare 50 kV and you go up to 100? Well, you get 50 over 100 cubed, but it's in the denominator. So now you get 1 over 1/8, or clearing that fraction in the denominator, you get 8 times more frequent. Okay, so that if you go from 100 and go down to 50, okay, the final is 50. The initial was 100. Look at the little relationship down at the bottom of the slide. Put the final in where you go from 100 to 50, 8 times more frequent. What if you do both of them? Well, if you get 8 times more frequent, and the other one gave you 8 times more frequent, then you get 64 times more frequent. So the combination of going to lower energies and changing these atomic numbers give you these various variations. On the boards, they've promised not to give any nitty-gritty little calculations like these, but the concept, and emphasize the concept. Concept number one, in mammography or in any a diagnostic test that requires a soft tissue differentiation, go to low energies. Low energies will differentiate low atomic number tissues. Soft tissues have very little differences in atomic number, so it behooves you to go to low energies. Okay, that's the concept. Okay, definition of subject contrast. Remember that we did that early on. I just wanted to make sure you had a good handle on that. It's just the ability of tissues to distinguish itself from the surrounding tissues, and that difference depends on the X-ray intensity emerging from the patient in the shadow of the various tissues. So again, you have that Z cubed over E cubed, and now we just want to make sure you understand why in mammography we go to low energies. I've already mentioned it, but here's a graphical way of showing it. Okay, and here we have two tissues, a high atomic number, low atomic number, and at high energies, notice there's hardly any difference between the two tissues. Okay, at high energies. But now let's go to lower energies. When you go to lower energies, now do you see that you're developing differences between those two tissues as you go to lower energies? So while at A, there was hardly any difference, in other words, subject contrast was very low, at B, now you're developing more of a difference. At C, an even greater distance, and the contrast is going up as you go down in energy. So now I'm showing you a graphical demonstration of that concept. Lower energies enhances the differentiation of atomic number differences, okay? And will increase the subject contrast, okay? Here's another very important a feature of the photoelectric effect. It's the basis for the contrast agent effect. You know that there's various tissues that you cannot differentiate in normal radiography. You cannot see blood vessels in the soft tissue. You cannot see blood vessels in the heart. You can't see blood vessels in the kidney. You can't see blood vessels in any soft tissue surround, because the difference in contrast is very, very slight. And down at the, look at the third bullet here, gray matter versus white matter. That is a very, very low subject contrast. And you certainly aren't going to go anywhere near differentiating that in a skull film in radiography. And you know that if you want to see tissues, for instance, blood vessels in a soft tissue surround, you're going to have to add contrast media. Let's talk about contrast media. Here's a patient, and there's a blood vessel, and X-rays incident on that patient. The X-rays go through that blood vessel. Blood vessels normally have very low subject contrast. They have an atomic number very similar to the surrounding tissues. But now you add contrast to it, and now given by that reddish blood vessel, and now that blood vessel will be visible. And it's because of that enhanced absorption in that blood vessel. Iodine did the trick of adding contrast. That's what we want to talk about. Iodine as a contrast media, barium as a contrast media. Iodine has a greater atomic number than the blood. And so therefore, it's going to absorb more. But it's even more than just the atomic number differences. Iodine, yeah. Has a higher atomic number? Yeah. Has a greater attenuation? Yeah. Will give you more contrast? Yeah. But there's another effect that really is an extraordinary, produces an extraordinary difference between that blood vessel and the surrounding tissues. It's called the K-edge effect. The K-edge effect. Let's talk about K-edges. Here we have a plot of the probability of photoelectric effects, just like the kinds of curves I've been giving before, but those before was for soft tissues. Now let's look at one for iodine. And what you see here is that as you go up in energy, at one particular energy, all of a sudden there's an extraordinary increase in the absorption of that radiation, of the probability of that interaction occurring, and then it trails off. But the idea here is that there is a very extraordinary increase in absorption at a particular energy. And that particular energy is at the binding energy of that particular orbital electron. And we say that there is going to be resonant absorption. When you match the X-ray energy to the binding energy, you actually have to go a little bit higher. But when you do that match, we have resonant absorption, where now all of a sudden there's a tremendous increase in absorption of that K-shell electron. Now, iodine has a K-shell of the binding energy of 33 keV. And so for this to occur, you really have to be a little bit higher. You don't want to be at the bottom here. You want to be at the top. So you got to be a little bit higher than the 33 so that you can be riding up on top of that extraordinary peak. So that let's now compare that with soft tissues. Here is your iodine with its big K-edge effect, and compare it with soft tissues. Now, soft tissues has a much lower atomic number, so that the probability of photoelectrics is much lower. And notice you don't see it as the way I've drawn it. You don't see a K-edge in soft tissue. Actually, all materials have a K-edge. A soft tissue, K-edge is at less than 1 keV. So it's way down here toward the bottom of the scale. And so we just don't draw it in. It's there, but in the a range of energies that are important for us, soft tissues do not display a K-edge. The K-edge is way down at low energies, so they don't appear. But now, in comparison, look at the conclusion, the result of this, the ability to distinguish blood vessels from the surrounding tissues is greatly enhanced, and you would have, you're riding way up on top over here with a big difference between soft tissues and, that tissue. There is your subject contrast over here between soft tissue and the peak of that K-edge. Okay. We said that we call this the resonant photoelectric effect, where this extraordinary absorption occurs, and you have to have that match, that resonant match between the X-ray energy and the binding energy. And you cannot be exactly the binding energy, because remember this idea here that any material will be transparent to its own characteristic radiation. You can't have that exactly the binding energy, because then there's no kinetic energy available for the electron, right? So if the energy in equals the binding energy, then there's no energies available for the electron to move away with. Okay, and you've probably have seen that that demonstration where a soprano hits a particular note and a wine glass shatters. It turns out that it's a very similar effect to what we're talking about here with photoelectric resonance. When the soprano hits a particular frequency note, and that frequency matches, there's the idea of matching, where that frequency matches the vibrational frequencies of the molecules in the glass, the molecules in the glass experience an extraordinary increase in absorption of the audio energy, of the acoustic energy, so much so that bonds are broken and the glass shatters. Very similar effect over here, except that we don't have a glass shattering. What we have is X-ray energy just being absorbed. Okay. The question comes up, when you choose a contrast material, the trick is to choose a material whose energies are, the binding energy of that contrast material matches the energies of the X-rays that you're working with. So if you back up a little bit, let's back up a little bit to this here. Remember we saw that the KH was 33. Why do we use iodine for contrast media? Why not use something else? We want to make sure that the KH falls where most of the photons are in your X-ray beam. Remember the typical X-ray energies we use is in the 30s and 40s. And so the reason we use iodine with its 33 is right in the middle of where most of our X-ray photon energies are, so that you then have more photons with the appropriate energy to produce this contrast effect. Okay, so same thing with barium. Barium has 37 keV as its binding energy, and that also is smack in the middle of where most of your photons are in a typical X-ray beam. The 37 is a little bit higher than 33. Why do we not use iodine in a barium swallow study or in GI contrast needs? Because when you use barium, you're lining the lumen with the barium, and there's much more absorption within the barium, and as compared to iodine in a blood vessel, so that you have to have enough penetration to go through the contrast material. You have much more clumping of barium as compared to the dilute solution of iodine, so you need more penetration. More penetration means a higher energy. 37 will give you a higher energy. Okay, so the question then is, how about in fluoroscopy? How about in mammography? In mammography, the ideal contrast media would have a binding energy of 20 keV. Well, yeah, molybdenum gets that, but that you would want to inject molybdenum into a patient. So there's essentially no good contrast media available for mammography. But yet we use iodine as the material, ductography, galactography, and it's not ideal. You haven't gotten resonant absorption. You're not utilizing the K-edge. But here I just want to demonstrate that even though you're not getting the K-edge contrast, you are getting enhanced contrast. I noticed that it's now past the normal time, so I better wrap this up. We lost some time there. Do you have a couple of minutes, or you got to run off to your clinical assignments? Well, let's wrap it up. Let me just finish up with this slide and call it a day here. What we're saying is that you still have contrast. Even though you're not utilizing the K-edge, you're using the Z cubed over E cubed, and there is still a Z difference between iodine and soft tissue, so you will get a contrast. And it is a significant, not as significant as it would have been if you were able to use the K-edge, but significant enough. Well, let's stop at that point. We'll pick it up again the next time. You all have a good day.